Hello, I welcome you all. The problem reads a pitching machine throws a ball towards the wall with an initial velocity of 10 meters per second. As shown, determine the velocity at which it strikes the wall at B and the velocity at which it rebounds from the wall. If the coefficient of restitution is zero point 0.5 and the distance is from the wall to where it strikes the ground at C. Right, so this problem is coming from the Engineering Mechanics and Dynamics of 14th edition by R.C. Hibbeler. So we have a ball here that is ejected, and the question is to find the velocity just before it strikes the wall. And when it collides with the wall, okay, since we are dealing with impact, and I guess we all know what impact is. Impact occurs when two bodies collide over a very short period of time. And as this happens, relatively large impulsive forces are generated that interact with these bodies that collide. An example is a hammer striking a nail. All right, so we are going to deal with this particular problem in parts before collision or before impact and after impact. So we are going to, like when you look at this particular problem, we are employing most of the things that we've done in the past. We are going to bring back the kinematic equations. All right, remember these. V velocity is time derivative of displacement. Acceleration is time derivative of velocity, and then a derived equation from the two, making the t subject the formula. Then we have this. From these equations, we can have a number of them depending on the boundary conditions. So for us, we want to use this equation where acceleration itself is constant, okay, at time initial equal to 0, and then s displacement initial s naught, velocity initial v naught. So we have this, okay, and that's ACT, and we have also this, okay, 2 AC is for constant, and then we have S minus S naught, right? So what we have here, so here we expect two parts. We are dealing with vertical motion as well as horizontal motion, and we know that horizontal motion here is constant. So here we have V. We have VAX, which is just equal to 10 sine 30, right? And this is just equal to 5. Then here we have, this is VAY, sorry. This is VAY. And then we do have VAX here. This is just 10 cos 30. All right. So let's call this one here as our reference for our first part. Okay, so what do we do here? So let's say before impact. This is the first part before impact. All right, mind you, we want to find velocity of the ball, right? So let's now look at the horizontal direction. So here this is our reference, like so. Okay, this is our x and this is our y. All right, so let's look at the x direction. Let's look at the x direction. So here we intend to use this equation s naught plus v naught t plus half ACT squared. Horizontal AC just becomes 3. Our S naught is 0. Our V naught is just equal to VAX, which is equal to 10 cos 30. And then we do have our AC here is equal to 0. Of course, we are looking for T to allow us to find VX, VBY, right? So with this, we can therefore write this equation as just 3 is equal to 3 cos 30 degrees times T. And therefore our T, which is just going to be equal to T, this is the time the ball takes to move from A to B. So we'll call it TAB. Okay, and this is just equal to Sorry, this one here is 10. Okay, so we have 10 cos 30 and 3 divided by that. This gives us this time 34.64 seconds. So this is the time it takes. This is the time it takes. And then from here we also know that our V itself just equal to V naught plus ACT. Okay, and since this is equal to 0, our V is just equal to our V is equal to 0, and our V here we just say this our VBX. Our V is just equal to VAX. Okay, and therefore our VBX, which is equal to VAX, is just equal to 10 cos 30. So our VBX, and this is going in this direction like this, is just equal to 10 cos 30. This gives us 8.6603. This is in meters per second. So this remains constant, right? So it's always constant. This is constant. Okay, it's constant. So I need to emphasize this. This is constant along the horizontal direction. Right? So this one is constant. Right. So now let's find our VB. We use the other equation. V is equal to, again, V naught plus ACT. Let's go to the horizontal vertical direction. Okay, so here we are here. We are on this direction. Okay, so we say Y direction so that we don't get confused. We need to move together. So here we use this equation. V is equal to V naught plus ACT, where our V here will be equal to VAY, which is equal to 5, and AC is equal to minus 9.81. Acceleration to gravity, and T here is equal to 2AB, which is just equal to 0.3464. And therefore, and our V is just equal to VBY, and this is equal to 5 minus 9.81 by the time 0.3464, and therefore our VBY is just equal to, and this is going up, this is equal to, that's 5 minus 9.81 by 0.3464. This we get a 1.6018. Okay, this is meters per second. So there we go, something like that, and we have the resultant. Expect the resultant maybe to be closer to that, right? So this one is VBY, and this 1.6018. Okay, and this one is VBX, and is equal to 8.6603 meters per second. And then this one is VB, and is equal to just the square root of VBX and VBY, right? And if we did that, this just becomes equal to 8.6603 squared plus 1.6018 squared. Square root of that, we have 8.8072. Okay, then we have theta itself. Theta is just equal to tan inverse of the y component, which is vby divided by vbx. Therefore, our theta is just going to be equal to 8.6603 divided by 1.6018. Okay, and then 1.6018 divided by 8.660. Okay, so this we get a 10.49, which is this one here. This is our theta, and this we can also represent it like this. All right, so this is the summary for A. This is the summary for A, and we found A, which is the velocity. Okay, so now we need to move to B, and B, we are dealing with velocity after it rebounds from the wall. So we've been given the bouncing coefficient, or coefficient of restitution, right? So let's go to the next page. I've tried to cut this section out. L is equal to 0.5, and this is just going to be equal to B B2x. It's along the x direction minus BW 2 x, all right, divided by VW1 x minus VB1 VB maybe I write them properly. So this one is VBX2 minus VWX2 divided by VWX1 minus VBX1. Right. So we know that this here, the wall itself here is velocity is 0. This also here the velocity is 0, and therefore our 0.5 is just going to be equal to VBX. What is our VBX2? We don't know it. Okay, and divided by VBX1 is just 8 point minus, is a minus there. You see this minus 8.6603. Therefore, our VBX2 is just going to be equal to 0.5 by 8.6603, and this gives us minus 4.3302. Okay, it's 3302, okay, meters per second. So our VBX2, you can write it as just 4.3302 meters per second, and it's going in this direction. All right, and then for VB Y2, this is just going to be equal to VB Y1, and this is equal to 1 point, this is 1.6018 meters per second. So with this in mind, we can simply say, let me just create a bit of a boundary here. So this we can simply say our B therefore here, and the reason this is because the line of impact is along the X and not the Y axis. Okay, so therefore, if we are to write this, we have the following, going to have something like this, something like this, something like so, and then we have the resultant, and we expect the resultant to be closer to the X. So let's say something like so. So let's label this. So this one is VB, this is V, this is VB X2, and we say this one is equal to 4.3302 meters per second. This one is VB Y2, so you got 1.6018 meters per second, meters per second, and then this one is the resultant VB, right? This is after collision. Then we do have this angle here. We have that angle there. Okay. This one is just equal to square root over VB X2 squared plus VB Y2 squared. And therefore our VB there is just going to be equal to 1.6018 squared plus 4.3302 squared. Then square root of that, we do have a 4.6170 meters per second. And then we do have theta. Theta is just tan inverse, and this is just VB Y2 divided by VB X2. Theta therefore is just going to be equal to 1.6018 divided by 4.3302, and tan inverse of that, we do have this, and this is just a 20.30 degrees, and it is like that. All right, so this is our B. I guess we are partially done with B. All right, so we are still, we are on part C, still after impact. Okay, still after impact. So what we need to do here is we're being asked to find this, okay. So we've calculated this. If you remember, you know what this is. This is our VAY, and it's equal to 5, and this one is our VAX. This is our VAX. Remember, if you've forgotten how we calculated this VAX, and it was equal to 8.6603, right? That's 10 cos 30. Okay. And then here, this distance here, okay, so this one we know it is 1.5. This one is, let's call it H. Okay, then let's call this S, or we just call it H1. Okay, so let's find this. So for us to find this, we can use this equation. S is equal to S naught B naught T plus half AC T squared. So our S here is equal to H. The idea is once we found this, we want to use it to find S, and then we have S naught, which is just going to be equal to 1.5, and then we do have our V naught, which is just equal to VAY, and is equal to 5. We have T, if you remember, we said TAB, this is 0.3. We calculated this in the previous sessions, and our AC just minus 9.81. Therefore, our H is just going to be equal to 1.5 plus 5 by 0.3464 minus 0.5, 9.81 by 0.3464 squared. Then H is just going to be equal to 1.5 plus 5 by 0.3464 minus 0.5 by 9.81 by 0.3464 squared. So this we get a 2.6434 meter. So this is what it is. Of course, we are using the reference A. A is the reference, right? Now we need to move on to the next step. So using B is reference, we're going to use this equation S naught S is equal to S naught plus V naught T plus half AC T squared, and our S is just going to be equal to, our S is equal to minus 2.6434. Our S naught is just equal to 0. Our V naught, we are in the vertical direction, is just equal to VB Y2, which is just equal to 1.6018. Our T, we don't know it, that's what we want. Our AC is just minus, like so. So writing this, we'll have 2.6434 equal to 0 plus 1.018 T minus 4.905 T squared. Writing this, this just becomes 5.905, okay, minus 1.6018 T 6434 equal to 0. So using the quadratic equation, this just becomes minus 1.6018 plus or minus minus 1.6018 squared minus 4a plus 4.905 minus 4ac 2.6434. Okay, and then divided by 2a. Okay, this therefore T is 1.6018 squared plus 4 by 4.905 by 2.6434. Okay, and then plus 1.6018 divided by 9.81. sorry, 1.6018 squared plus 4 by 4.905, 2.6434, then square root of that, then plus 1.6018 divided by 9.81. So we do have the time, which is just 9.9153 seconds. So this is our TBC. This is our TBC, which is this particular time. All right. So now using again S naught equal to S naught plus V naught T plus half AC T squared in the horizontal direction. Our S in our case is just equal to S BC, and our S naught is equal to 0, and then our V naught in our case is just equal to B is equal to B x2, which is just equal to 4.302, and our AC is equal to 0, and our reference here, our reference is B. So if you wrote this just becomes SBC. This is equal to V naught, which is just equal to 4.3302 times time. Our T here we said is 0.9153. So by 0.153. Okay. What else? This is about it. Therefore, our SBC here is just going to be equal to 4.3302 by 0.9153. This we get a 3.9634 meters. I think this is about it. We found the distance itself. Okay. We found the distance in the previous case. We found this part here. This is the whole solution. This is the solution for the other part. Okay. So this is the part. This is the solution for the other part. And then in the other part there, of course, this was the solution. Okay. So then let me move on to the next here. Of course, this was C. I think this is about it. I think we have solved this particular problem. We have addressed A, B, and C, and I hope this particular video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye-bye, and I'll see you in my next screencast.